Okay, so why functional programming? So a couple of words about myself. Oh, sorry, the goals. So what I want us to achieve in this meetup is that you understand the value of functional programming. Why is it? Why is it interesting? Why one should spend the time to learn functional programming? What benefits do we have? This should become clear at the end of the talk, during the entire talk. And the second goal is to leave you motivated to learn more about functional programming and then use it in your jobs, in your hobbies, whatever. A bit about me. So my name is Denis Krivitsky. I live in Germany. I live in München. I'm coming out from Israel. I grew up in Israel and I studied computer science. I have a computer science degree, master's degree. And I'm very passionate about programming languages. During my career, I became familiar with the following languages, just to give you an overview. It's just because I enjoy learning them. I do this in free time. this is how I spend my free time, by learning new languages. After seeing all of this, I came to the conclusion that functional programming is my favorite thing. And when I speak about functional programming, my worldview is influenced very heavily by Haskell. This is where I take my inspiration from. However, this talk is not about Haskell. This talk is about the principles which could be applied in any programming language. So, what is functional programming? I frequently ask this question, my colleagues or my friends, and every time I get a completely different answer. And if you Google and you try to Google this answer, you will also get a lot of answers which are contradicting one another. So there's no common definition. And the definition that I'm going to provide you here, this is what I think it is. This is my take on it. So functional programming is programming with functions. But when I say programming with functions, we should first of all define what do I mean by a function. When we speak with a software developer and we say function, he usually means a function as in a programming language. When you ask a mathematician about what a function is, the mathematician would come out with a bit different definition. So this is a mathematical definition of a function, which is a mapping from one set which is called domain to another set which is called codomain. And that's it. That's how it's defined in math. So when I say that functional programming is programming with functions, I mean those kind of functions, the mathematical functions, not the programming language functions. Sometimes when we speak with software developers and we want to make to emphasize that we are speaking about mathematical functions, we also say pure functions. So let's see what follows. If I take the following example, print hello world, this would be a function in C or Python, for example. This is not a function as defined in math. Why? Because this function takes some argument, it takes a string, so its domain is the set of all possible strings. But where is the result? What is the codomain of this function? And this is not clear because this function returns nothing, it returns void. And in process of the execution produces a side effect. This is exactly why it's not a function according to the mathematical definition. Another example is this: x equals random something. So this function returns a value. It takes nothing in, and it returns every time something different. So if I call it twice, I get two different numbers. With the mathematical function, this is not possible. If I give the mathematical function the same input, I'm going to get the same output always. And there will be no side effects. So for people who just joined, welcome, thanks for joining. Please keep your cameras on. Please turn on your camera so that I can see your face expressions and see and have this conversation bidirectional. Okay, so let's go on. What are the advantages of functional programming? So if we write our code only using those pure functions, what are we gonna have? And the answer is very simple. The advantage is modularity. We're gonna have modular program. Is it important for the program to be modular? Really, how important is it? Okay, what is exactly modularity? Modularity means that we can divide the program in several parts. For example, this whole program is consists of part 1 and part 2, and those part 1 and part 2 is somehow glued together to create the whole program. So the part 1 and part 2 are the modules. It could also be, of course, reused in other programs. Thanks for turning on the cameras. In functional programming, we have two kinds of glues that are necessary for in order to program with functions, and they are higher order functions and lazy evaluation. The higher order functions glue means that function is a first-class citizen, that we can pass functions as parameters to another functions, and in this way create even more complicated functions. So this is the meaning of higher order functions. And lazy evaluation means that we do not evaluate the arguments to every function when we call the function, but we leave the evaluation for later in the hope that we will not need some of the arguments, and then we will spare the time evaluating them at all. And this is possible because we have no side effects, and it doesn't matter when exactly we evaluate something. It doesn't matter if we evaluate this freer or later. The result is the same, and nothing is ever impacted by this. In imperative languages, this is of course not the case. Okay, so what we get from modularity? Those are the outcomes of modularity. So if the code is modular, it's going to be reusable because you could reuse the same module again and again in different parts of your system and different systems maybe. But if we used many of our code, then we have less code in general. And if we can reuse the code, probably the code becomes more testable, because unit test is actually just another use of the same module. Like we reuse the production modules in unit test environment in order to test them. So if they're reusable, they are also easily testable. If they are easily testable and there's not much code, then we have less bugs. And another advantage of modularity is that the code is now easy to understand, because as humans, we are not capable of reading 100,000 lines of code at one bunch. We need to focus only on small parts of the code in order to understand them, to somehow understand what they do, and then switch to another model and be able to forget the previous one. So if the code is modular, it's much easier to understand what's going on there. And it all comes to ability to write code with less bugs, or to create much bigger programs which is what we want, because we rely on software more and more in our lives. Now we use software in order to speak with one another, and we will rely even more in future. Therefore, we need the software to be even more stable, and the systems need to be even more complex. And I see functional programming as one of the ways to make this next level of next level of complexity, next level of stability possible. So in this talk, I'm going to show you an example of the same algorithm, which is once implemented as a functional code, and another implementation implemented imperatively to compare between the two. And I will show you that the imperative code cannot be subdivided into sub-modules. It's one piece, undividable. And the functional code can be modularized. Of course, in order to show you an example in this talk, in this 45 minutes talk, I must choose a very, very small, unrealistic problem. Because every realistic problem will be just too big to show in such a meetup. And you will need to trust me that the same principles applies in realistic code as well. And it applies even more than in this small code example. The bigger the code is, the more benefits we get from this approach. Now, in order to show you the functional and the imperative code, I will need to write this code in some language. So I choose Python to be the imperative language because it's very simple and it's very popular. People, you probably know Python. You can read the code easily. For the functional, I choose Haskell because this is the origin of the functional programming languages, so to say. But you don't need to know Haskell. I'm going to explain everything I show. I will explain enough to understand the examples. But first of all, let's start with some outcomes from using functions. So first outcome of using functions, here you can see Python code, is as follows. Let's see some examples. Def f of x return x plus 1. Okay, this is a function. This is a pure function. It's clear what we do here. It's a positive example. Now, a equals 1. This is a variable assignment. Now, if we try to use a variable inside of another function, h, what happens is this is like another argument to this function, a hidden argument, because I can change the value of a and the value of h will also change. So this will render the h as not pure anymore. Therefore, this kind of variable use will be not allowed in functional programming. Let's see another example. I'm sorry, I explained it differently. This is an assignment. Okay, so inside of h, I assign a 2 to a, and which means I had a becomes somehow my result from this function, which is hidden, not explicit. That's why it's a side effect. That's why it's forbidden. And this example is when I read from a, and the return value of g is going to be dependent on a, and a becomes somehow a hidden variable, which is also forbidden. So both of those uses are forbidden. Now let's try to see if what else we can do with variables. So the first line, b equals f of 1. And then we have b equals f of 2. So we reassign the variable. In this case, if f is pure, we can just remove the first line because there were no side effects. And then B is more, it doesn't function as a variable anymore. It functions more as a constant. Now, another example. If we store something in C, then we use C. Up until now, everything is fine. And then we use C to store something else. Well, that's functional. There's no side effects, but we could just choose another name for this result. We just try to reuse the memory, the same memory for a different result, but the compiler will optimize it anyway. Let's see what, so this goes away, okay, this didn't go away yet. No, the first two. Now, if you have a loop and we run 10 times this loop, inside of the loop, we run f of I, and f is a pure function, and store the value in A. So the next iteration will overwrite A and leave the previous iteration useless because there's no side effects and they lost the return value. So I could just remove this whole and just replace it with a single last iteration. So this use of variable also goes away. If I just call some pure function inside of a loop without assigning it return value anywhere, it's totally useless because a pure function makes nothing else except the return value. So this goes away as well. But what if we have something like this? We sum up an array and we have this accumulator outside the loop. Well, the whole for loop actually behaves like a function with side effects affecting this sum, and side effects are forbidden, so this goes away as well. So the conclusion that is as follows: variables are useless, so we can just remove them from the language or just not use them. Functions with zero arguments could actually represent something useful in functional programming, and they could represent constants. This is a function that takes no arguments and returns something. We could use this function as for pi. It's useful. It doesn't change. It's always the same. It could be equivalent of storing this value in the variable pi and somehow manually never changing pi. The Python is a language cannot help us with this. It allows this change. We need to be disciplined. So this is another example of a zero variable function that uses another function, which is of course also functional. It's useful. Is another function. It's not a zero variable function anymore. It's one variable. It uses both of those inside of the implementation. That's perfectly fine because those never change, and this function also never changes. Now, I want to introduce you to the Haskell programming language. And here's what we have here. Here is the equivalent code in Haskell, which is exactly the same as this code in Python. By the way, can you see my mouse pointer? Sure. Good. So in Haskell, we have no variables. We have only functions. And this is a function definition. This is a function with zero variables. Therefore, it cannot be changed after assignment. Those two statements are equivalent. Now, here's how we define in Haskell a function with one variable. We don't need the parentheses here. This is the function name. This is the variable equals, and then we have an expression which is the value of this function. If we want to define function with two variables, we just put two of them, one after another, delimited by spaces, equals what we want. We could also define anonymous functions in both languages, in Python and in Haskell. Here, in this line, the function is called h. This is the function name. And this line defines the same function, x plus y, but does not give it a name. It's useful when we want to give this function in some variable, to some other function. And how we apply functions? Well, to call a function, we write the function name, space, first argument, space, the second argument, and fill the argument, and we get the value. Let's play with this a bit. I prepared some demo we can play with the Haskell interpreter. So this is how it goes. F equals 1. F is 1. Now let's say g x equals 1. Now g is a function. Let me call g of 1. It's 2. G of 10. It's 11. Very simple. Now what I can do with lambda? This would be x, y. This would be a lambda expression, meaning an anonymous function, x plus y. But if I just run this, it's gonna be useful. It's gonna be useless. I could store this value of this expression in some variable, in some give it a name like this, for example. Here's my equal sign. Yeah. Now I can call h of 3 and 1, 4. Okay, works. Good. Let's go on. Now, of course, we need we learn how to define functions. Now we want to learn how to define data. Haskell is a statically typed programming language, and Python is dynamically typed programming language. Therefore, for the data, there will be no direct equivalence. Let's see. Let's start from the very beginning. Data is the keyword that defines data. Beverage is the type name, and then we just enumerate all the possible values that this type can have. In this case, 2 values, coffee and tea, this is any num. Yeah, we know this from most programming languages have this. Also Python, this is an enum. They are equivalent. Now, when we want to use a num, so coffee is a value of type beverage, we can put it in a variable. And let's play. Okay, demo 1. So we have beverage. In order to run the examples in Haskell interpreter, I need to be able to print out the value of coffee and tea to convert them to strings. And this keyword tells the compiler, hey, you go on and figure out yourself how to convert them. Don't ask me. So I'm going to load this demo 1. Here we go. And now A equals coffee. Here we go. A is coffee. I can put something else there. A equals, by the way, is the font big enough to see? Good. A equals T, perfect. A is T. A equals milk. No, the compiler will not let me do this because A can be either coffee or tea, nothing else. This is very good because there will be no illegal state. Only legal values can be there. Now, let's go on. We define another data, another type, visitor, like when we build a website. The visitor could be an anonymous visitor or a signed-in visitor. And if it's a signed-in visitor, I also want to know his username. So every case of the enum can have an associated value or not have an associated value when we don't need it. So anonymous, no value, user, yes, the username. In this way, for example, if we do this in Python, we must allocate some variables, create a class with maybe a Boolean which says it's anonymous or not, true or false. And when an anonymous is true, the username field is there and its value never used, should not be used, but we could by mistake put something there and use it by mistake and so on. In Haskell, this will not be allowed. So This is how it works. In order to put anonymous in a variable, just like coffee and tea, and in order to put the user in the variable, we use the constructor, and then we write the string. So v2 user John, we could define v3 user Dennis. Here we go, we have v3. What if we try to give user without a username? Ta-dam. The compiler says v3 is a function. When you give it a username, then it will be a visitor. But right now it's just a function. If you try to give it an integer, no, it's an error. It must be string because we say that it's a string. Okay, now the next question would be, of course, how can we, if you have v2, how can we get the associated value? In order to get the associated value, we need to use destructuring or pattern match. And pattern match in functional languages is the basic language primitive. For imperative languages, the basic language primitives are variable assignment, for loops, if, then else, while loop. Those are the basic stuff for functional languages. The basic stuff is functional definition. We define a function, and pattern match. We destruct the values, and using those primitives, we can build almost everything else. So let's see how. When we define function, we could define a function in the following way. We could say function f. First of all, I'll give you a simple example. We defined this function before, f x plus 1. So this is simple. We already saw that this works. Now reload, f of 1 is 2, everything simple. Now I want to make an exception. I want f to add 1 to every number except 10. But when I get 10, I want the return value to be -1. Now I can do this. That's it. So f of 1, it's 2, fine. F of 9 is 10. F of 10, -1. So the compiler, so this definition, the definition of a single function could take several lines, and the compiler will first of all see, does the argument matches this one? If yes, then this is the result. Otherwise, it goes on, and x can match everything. Well, everything can be inside of x, and then this is the value. In the same way, we're gonna use pattern match. I could say a cost of price of coffee is 10. Price of tea is 20. Perfect. Now I have a price function. Very easy. Very price of coffee. Perfect. Works. Price of tea. Price of milk. Error. Milk is not beverage. We caught the error. Good. Now let's go on. What do we want to know? To know about the visitor? Maybe we say trust level. Trust level of a visitor. Do we trust them? Anonymous. Oh, the trust level is 0. We don't trust him. Trust level of. Now, here I want to use the case of user. So trust user, and then I can give a variable. A variable name is a variable. So if the argument is a user, this value v2 will be destructured into its constructor name and the value inside. So that's how I get access to the value inside, to the string inside. Name is the string. Now, and then I say, okay, length of name plus 1. The longer the username, the more trust I have in this person. So trust level, anonymous, 0, good. Now I need parentheses here, user, Dennis, trust level is 6. This is how I make this structuring. Good. Do you have any questions? Can we move on?
I've got a question. Do you have to define trust level in following lines, 15 and 16, or can there be something in between? Does it have to be one block?
One block, successive lines, nothing in between.
Okay.
Okay, good. Now let's go on. Here's my presentation. So we covered this. Here I finished the introduction of Haskell. Now let's see the example. Now let's see the algorithm that we're gonna take apart. So this is how it looks in Haskell. So this algorithm takes a list of integers and sums up their values. Very simple. It's a sum of an array of integers. So how we do this imperatively? We define a variable result, and then we run through the list and add up every element to the result and then return the result. I think it's clear, right? Now you could start thinking, how can I divide it into submodules? Is it possible to divide it in parts? Okay, so the example, the choice of this example is intentionally so simple, so that it's hard to divide it further. Okay, now let's see how we do this in Haskell. So first of all, we need to define list. And this is how we define list. So list is a data, and so it's going to be a list of, because we don't want to define list of ints or list of doubles or list of strings. Let's define list of anything. So A is type variable, can take any type. And it will be in an enum. It's either a node or nil. Nil means empty list at the end. Node means node has two associated values. So we can have as many associated values as we want. Now it's 2. The first value is the element that we want to store in this list node of type. It's type A, any A. And then we need the rest of the list here. So it's a list of A. Of course, it's a recursive definition. And at some point, this list needs to be ended with a nil to end the recursion. Now, let's see how we implement sum. So, as we already saw, we have 2 lines. The first line will take care of the nil case. If it's empty list, we say the sum is 0. It's our choice. Otherwise, it's going to be a node. And then by restructuring, we extract its head and tail. So tail is a list and head is an element. And the sum is equals to head plus the sum of the tail. Let's play with it. Let's make sure it actually works. So here I have a list. Let's load this file into my interpreter. Here we go. Now let's implement sum. So sum of nil is 0. Sum of node of head and tail is head plus sum of tail, right? See if it works. So sum of nil of an empty list, right? let's create some list. L1 is our list. Let's put it, oh, let's create a list here so we can use it later once again. So this would be an empty list. It's too simple. We are not interested. Let's create a node, and then we have element 3 and then an empty list. Okay, that would be a list with one element. Let's create another element 2, and this is going to be the tail. Okay, let's create another node 1, and this is going to be the tail. Now we load, let's see, L1. Yes, this is a list with 3 elements. Let's see if we get its sum. 6, good, works. Okay. So up until now, this is the imperative implementation. This is the functional implementation. Can you destruct this or subdivide this imperative implementation into sub-modules? Do you have an answer? Okay, I guess no. Thanks for having no answer. Okay, let's see what we're gonna do. How we're gonna divide the functional implementation. So let's take this 0 and this plus operation and extract them away. And this is what we do. Now I'm gonna use a more general way to sum the numbers. This is the same sum that we saw before, just for reference. I'm gonna define a more general function, which is called reduce, where the 0 comes as an argument. So this function gets append, which is the plus or something else instead of plus, and empty, which is the 0. So reduce with append and empty, and the third parameter is our list, and the list is now we return empty instead of 0, which means like this is the beginning of some calculation. And then in case of node head and tail, we return append head. So we sum up the head and the result of applying reduce to the tail. Now we can implement sum by giving reduce this operation plus and the 0 value. This will be a sum. But if we have this sum, we could also use reduce as follows. We could also, using the same reduce, we could also create product by giving it 1 and a different operation, and then it's a product of the array. We could also calculate the length of the array. So this is the function. Okay, here we use anonymous functions. So it's going to be x plus 1, and we start from 0, and then we get the length. So look what we've done here. We subdivided this sum into four components. One component, into 3 components. One component is the plus, another component is 0, and another component that combines them and traverses the list. So this guy is responsible for traversing the list, and those guys are responsible for summing up the values. If I use with the same traversal function a different pair of values, I get another implementation of another product, and then those guys give me length. So this is reusability. Shall we do this interactively? Okay, cool. Then let's do it. Reduce. So reduce gonna take two parameters, append and empty. And the third parameter is our list. In case we get nil, empty list, what we're gonna return? Who can say?
Reduce itself?
No, it's a start. Like this is like a zero. If the list is empty, there's nothing to sum up. It's gonna be empty. Like empty was zero when we used sum. Empty, right? Now, if we use empty now, the case of node, when we have a node with an element head and the tail, what we're going to return now? So we need to combine the value of head, right? And the value, this value, so we have head and we will call reduce recursively on our tail. In order to call reduce recursively, we need to give it the append, which we just pass forward, empty, empty, and the list, and the tail of the list. Now, we need to combine this guy and this guy together. How we can do this? We have this append function that combines them together. So we call append, and append will get head as the first argument, and reduce, and the result of this expression as the second argument. By the way, I can put the arguments in new lines if I do, if I tabulate them. The syntax allows me to do this, like to write it like this for readability. It's exactly the same as putting them in the same line. Okay, let's see if it works. Load, reduce. Now, let's do sum. Okay, we need to create sum, right? So we have already sum here, so I cannot define function sum once again. I need to give it a different name. It's going to be sum2 then. Otherwise, it's a compilation error. It's reduce, plus, and 0. I need here the parentheses because plus is an infix operator in Haskell, and when I put it in parentheses, the compiler knows that I want to relate to it as a function because it's function. It's a syntax, and 0 is just a value. So now let's see. Let's see, sum 2 of L1, 6, works. Sum 2 of nil, works. Let's do product. Product. It's reduce, multiplication, and 1. Reload. Product of L1. Error. Because product is defined in the library and I need to hide the library product, I guess. Let's see now. Yes, this line hides imports from library so that they do not interfere with our code. Now, yeah, it's 6. Is it 6? 1 by 2 by 3. It is 6. Let's make something bigger to make sure we have different results. Product of L1. 60. Yes, it works. Product of nil. 1. So let's see what we have up until now. Up until now, we destructured the sum into something that combines value, something that starts the sequence, and something that traverses the list. we saw that we could replace this pair with another pair and get different functions, different usable functions. What if we replace reduce with something else? Like, what if we need to traverse something else, not a list, like a tree? Could we traverse a tree? Let's see. So here is a tree. So how a tree is defined, a binary tree? Well, it's very, very similar to list. So it's either nil, it's either an empty tree, which is very simple, or it's a node, but here we have 3 associated values, not just 2. First value is the element that we store in this node, and then we have 2 subtrees, right subtree and left subtree. And it's recursive, of course. Yeah. So we need another reduce function. This reduce is a bit more complicated. The first case, if we get reduce, append an empty, and we get an empty tree, we return empty. This is simple. There's nothing to sum up. We start up. But the second case is more interesting. We have a node, then we restructure it into 3 variables. X is the value, is the element that lives in this node, and then we have left subtree and right subtree. This syntax lets us introduce local variables, local constants, local definitions. So we define another value, local left r. It's like the result of reducing the left tree, like left sub result. So we call recursively the reduce. We just pass forward append and empty and give it the left subtree. The same with the right. Now we need to combine this left r and x, these 3 of them together. So in order to combine the 3 of them together, we call append twice, because first of all, we combined left and x to get a single value, and then we combine the result of the first with the right, because append takes only 2 arguments. That's why we need to apply it twice. Here's our sum. So sum of all the values inside of a tree is going to be this. This reduce tag means reduce for trees, because we already used the name reduce for list. So in order to not to clash, it's just another name. There's nothing special about this tag here. So sum is reduce of plus and 0, and product is reduce of multiplication and 1. And now we've got another useful thing. Okay, now we have actually I have a mistake here in the slide. This one of them should be reduced and one of them should be reduced tag. So we had different reduce functions that reuse the same combination and start value, and the whole thing is useful. Yeah, one works on trees, another works on lists. One makes product, another makes sum, another makes list length, and so on, so on, so on. This is how we can combine the models together. Do you have questions? Shall we do this, code this interactively? Shall we code this? Or is it? Okay, so we will not code it. Okay, good. Now let's go on. So what I say actually is that using this functional approach, we get much less code, and I want to show you an evidence of this in practice. So, U.S. Navy Naval Surface Warfare Center wanted to compare the productivity of different programming languages, and they made some research. And in order to compare the productivity of languages, they made a list of languages and combined some problem that they wanted to solve. And their problem is, of course, has to do with what they do. There's some ships floating, there's some radars, there's some attack radius or detection radius of objects flying on the skies, and some regions need to be calculated and so on. So we'll not go exactly what needs to be done, but there's some problem. And they gave it to 10 people, to 10 people to implement this, and counted the lines of code and the development time. And let's see what we have here. So we have languages like C++, which this is a bit outdated. I mean, it's quite a long time ago. So some languages do not already exist, or not used anymore. And let's see. Haskell resulted in 85 lines of code and 10 hours of development time. And C++ resulted in 1,105 lines of code, and they didn't measure the time. Ada, it's another imperative language, 800, 250, and so on. So if you compare it with C++, it's more than 10 times the difference. So, but see here, there's another line for Haskell. So Haskell appears twice. And the story is as follows. When the first 9 results were ready, there was a commission to review the results. And when the commission was presented with the Haskell solution, it was a file with a lot of comments and code. And they looked at the comments and they could read the comments, they could read the code, and they said, well, we see this is the documentation, this explains how it's done. Where is the implementation? Where is the code? No, this is the code. It actually runs. We know that it looks simple, but no, that is the code. Very short. So they said, we don't believe it. Let's make another one. Let's find some. There's something. Something is not realistic here. Let's find another person who could do it once again in Haskell, and that's why we have the last line. So they found a student who didn't know Haskell, and they gave him 1 week to learn the language. And after 1 week, after he learned something about the language, they gave him the assignment. He completed the assignment in 8 hours, and it was 156 lines of code, which is the second best result. And what do you think was the response then? They didn't. They just said it cannot be true, and went on with something else, with C++ or what, I don't know. they didn't choose Haskell. So to conclude, functional programming is a programming with functions, with pure functions. If you program with pure functions, you don't need variables. They become irrelevant. Or in other words, all your state is going to be immutable. You have no side effects. All this results in modularity. Your code is much more modular. This results in more productivity. So use functional programming, learn functional programming. Now, I know that using functional programming in your job sometimes is not that easy, because your company may have some policy about the programming language and how to write code. So we at Visonum use functional programming for our daily programming. So if you want to use this technique, come join us. Come join us. Look at our open positions and contact me if you have interest. Thanks for your listening. Now we have time for Q&A. or just open discussion?
So, I have a question.
Sure.
So, from what I'm understanding, functional programming is a technique to be used in any language, right?
Yes.
Or is it something specific to Haskell, or Haskell does it easier, or it's meant to do functional programming throughout? That's why Haskell is like the preferred approach.
Yes. Yes. Exactly. You're right. You're completely right. Functional programming is a way of thinking. In principle, you can use functional programming in any language, because I showed you that you could use Python, and you could define, you could neglect all the variables and use zero argument functions, and you can be disciplined and make no side effects, and it's going to be functional. The disadvantage of using Python for functional programming is it's going to be verbose. Because the syntax requires parentheses and return, it's just going to take much more text. And the compiler will not help you keep the data constant. In Haskell, the language is optimized for functional programming. So it's much easier, it's much shorter. The compiler helps you along the way. And Haskell, you can also do imperative programming in Haskell, of course. But when you do imperative programming on Haskell, it's going to be very verbose. The compiler will be on the way. Yeah, you need to fight with compiler a bit. Yeah. So one is optimized for functional, another is optimized for imperative, but it's possible to do both in both languages.
Could you show the list of programming languages again from the beginning?
Of course.
And which of those can do functional programming?
This line is about functional. So Haskell, PureScript. PureScript is a dialect of Haskell, actually, which compiles to JavaScript, and it's made for web development, for UI development. ML is a functional language. Lisp is a functional language. It's actually one of the first functional languages. So it's very old. It was invented in the 50s, 50 something. F# is a functional language. It's a .NET language compatible with C#, compatible with all the .NET infrastructure. Racket is another type of Lisp, a newer dialect of Lisp. Here, Clojure is a functional language. It's also Lisp. It's a JVM language, runs on Java Virtual Machine, compatible with all the Java libraries if you need. So Haskell and PureScript, they are statically typed, and they are capable. They are very unique in their type system. They are capable of, the compiler is capable of checking if the function is pure or not pure. This is very rare. From this list, only those two can do it. F# is also statically typed, but its type system is not that strong and does not allow checking for purity of functions. Otherwise, very strong type system. Otherwise, yes. Lisp is dynamic. There's no types there. Racket is dynamic. Clojure is dynamic. That's it. Other languages, for example, Kotlin, Rust. What else? Kotlin, Rust. It's Scala, of course. Scala is also functional language. Yeah, statically typed functional language. And Scala is also not capable of checking for purity, but otherwise the type system is very powerful. So Kotlin, for example, and Swift, they stay somewhere in the middle. They have some good features that help very much the functional way, and they lack some features which are really needed to lack them. So they're somewhere in the middle. And C, I would say, would be the imperative edge of the spectrum, very, very imperative edge. And the languages with their newer version, as they evolve, like C++ still evolves, they get more and more features to bring them to functional ways. So C++ got lambdas, Java got lambdas, and there are steps in this direction. Also for almost any language with its new version gets some functional features. So, next question.
What about architecture patterns? Is there any need to define architecture patterns, or is it all just function trees or something like this?
Yes, good question. Of course, when we use functional approach, we need to use the approach in both levels. In the micro level, where we write the individual function, so on the code line level, so to say, as well as in the architectural level, so in the macro level. For example, if we develop an iOS application and we use UIKit, which is a model view controller architecture, the controller there is a mutable entity, and you can't go functional with this architecture because you need to mutate the controller to do something. You will be limited. There's another way to build the app. There's another architecture which is called update view controller, update view model, or the update model view. It's also called Elmish. It's also called Flux. It has different names. In this way, there's no mutable stuff there. There's only one single variable, which is a single exception to the rule, because we have to when we develop UI, we have to store some state somewhere at the end of the road, because if a user clicks a button and the button is now clicked, the system remembers this. So we need at least one variable, and Elmish architecture has this only single one variable that holds everything, and everything else is constant. Do you have more questions?
I think you just answered more or less what I was going to ask. Like in Haskell, you can do pure functional programming for mathematics, but as soon as you have user input or output, that would not match the definition of pure functional programming anymore. Like you have input that you take in a function, and it's a side effect. So that's all handled by this Elmish.
Yes, you're right. You're right. I didn't want to focus on side effects in this presentation in order to be on time. But in principle, when we program, when we write a program, the program needs to get some input to start working, to start processing something, and at the end to output some result. And both this getting the input and producing the result are side effects. For example, one example is as follows: if we have a program that makes compression, it takes a text file and compresses it like a zip compressor. this program would need to read the input file, and then it's a single pure function that takes in the file, produces the compressed output, and then we need to write this compressed output to disk. And reading from disk and writing to disk, those are side effects. Yes, and we must have them. We cannot ignore. I mean, we cannot go without. Therefore, in functional programming, the idea is that we keep the side effects to the minimum. So the minimum here is two: one function that reads the input, another function that writes the output. So in the whole program, we have two side effects. Everything else is pure. I mean, this is the extreme. Less than this, it's not possible. Without this, two would not be possible. And when we do user interface, then we need three exceptions at the minimum. So first exception is the input. Second exception, input, for example, reading the mouse, reading the mouse coordinates or button clicks from keyboard, or network packets from network, getting packets from network. This is the input. The output, we write to the display. We need to write to our GPU or to display buffer to show something in display. We send packets on the network. We write to files. This is the output. This is the second one. And the third one, we also keep internal state, because when the user opens a text document and writes some text, we need to save the text somewhere. Yes, and this is the third exception. So in principle, when we have interactive programs, we need these three exceptions: input, output, and this single state. Everything else can be pure. And this is the idea of the LMesh architecture. There are only three exceptions. And it's very, so of course, those exceptions and side effects, they have all the side effects problems. They have all the problems of side effects, but there's only three of them, and we know all of them by heart. It's not that hard to manage this system. Another question?
In which domains and in which industries is Haskell mostly used?
Just in general, Haskell is not widely used. It's a rarely used language. It's used on the server side mainly, and it's used on blockchain, heavily blockchain, and financial sector. Those, by the way, those areas which are very, very sensitive to bugs, to errors. For example, in blockchain, if you make an error and you want to update to the new version, you need to update all the nodes. This is an area which is very sensitive to bugs. In automatic algorithmic trading, where money is managed using software, this is also very sensitive because it'll be hacked. A bug could cost a lot of money. Yes, they use Haskell.
And so I assume that verification is also easy to do, or not? Verification of programs, algorithms.
Yes, good question. First of all, once we have a functional program, it's very, very easy to take the function and test them, because of this lack of side effects. I can take any function, give it the argument that the function wants, and then the function produces result, and now I can compare the result to my expected result. This is unit tests. But the functional programmers, they become very lazy very fast, and they don't want to write unit test anymore. And they invented an approach that is called Quick Check, which writes unit tests for them. They express the correctness of a program using invariants. An invariant could be, for example, in my function where I sum two numbers, the invariant could be as follows. If I take x plus y and x plus y, and then I add another one plus z to the result, this would be the same as taking x plus, and in parentheses y plus z. They should always be the same for any three numbers. So this is an code invariant, and they give this quick checker this invariant and say, now you go and figure out the inputs and outputs and check everything. And if you find that a bug come on, let me know what for what input this variant doesn't hold. But don't be bad. You go on and find the smallest possible input. Don't bring me numbers of the range of in millions and billions. somewhere around zero, I would like to see that breaks the algorithm. And in this way, a single invariant is equivalent to hundreds or thousands of unit tests. Why it's possible? Why people don't do this in imperative languages? It's because of side effects. Because the lack of side effects means I can call the function how many times, how you want, and there's no side effects. So nothing is changed. Nothing is influenced by this. That's why I can try on randomly different inputs. So this is about automatic tests.
One question.
Sure.
How easy it is to make certain parts of the code out of Excel and then the remaining in some other language? Like can that be done basically? So like the things that are highly dependent on speed as well as it has to be less error prone versus the ones that are input output. So something like that. Can that be done?
Mm-hmm. The answer for this question is the same as for any other language. There's nothing special about Haskell and interoperation with other languages. It's done as with almost anything else using C interface. So Haskell has a C interface. You can, yes, and through the C interface, you can interface with almost everything because C is a universal API, so to say, between languages. Haskell is capable, also Haskell is a purely functional language. It is capable of doing side effects. Okay, it's just that the compiler can check if a function makes a side effect or doesn't make a side effect. Yes, this is the difference. But if you tell the compiler, I want this function to have side effects, then you can do this. So you can interoperate with any imperative code, of course.
Okay. Thanks.
Guys, I would like to facilitate actually a discussion. So we can go on with question and answers. I don't mind. We could also start a group conversation where you speak or where you share something that you would like to share with others, or where you ask other people, so that we have this community build-up process. So let's make it free. Either ask questions, ask me questions, either ask questions something else, or just share something from your experience, from your lives that you would like to share.
And before you said Haskell is not very commonly used and shared your company. So do you actually program Haskell there? Or?
In our companies?
Yes.
We program in PureScript because we do some user interfaces, and Haskell is good for server side because it works on Windows, Mac, Linux. Haskell does not compile to iOS. Haskell does not compile to Android, unfortunately, because of practical reasons, because nobody ported the compiler to those platforms. That's why we do not use Haskell there. We use PureScript. PureScript is a Haskell dialect. It's built. It's a copy paste of Haskell with some minor changes, and minor changes to the better, to the good, let's say, with some fixes. And PureScript compiles to JavaScript, and the result can run in any browser. That's why we use PureScript.
Sounds similar to Elm. Have you tried that?
Yes, very similar to Elm, but Elm is very good for anybody who wants to start with functional programming. It is even better to start with Elm as with Haskell, because Elm contains only one half of the Haskell language, the easier half. Elm is not capable of producing side effects. So the whole type mechanism, which is quite complicated, it allows side effects in Haskell, does not exist in Elm. And side effects are handled by the Elm framework, which is somehow outside of it's quite a lie. Yes, this framework is outside of the language. But this arrangement makes the RAM pump easier. It's easier to learn, and Elm has quite a good documentation, quite a good manuals. So it's a good step to take. First of all, to learn Elm, and then to switch to PureScript or Haskell as a second step. You can also use Elm for web development. Just use Elm. That also works, but many things are not possible there, which I would like to have on my toolset. That's why we use PureScript.
And performance-wise, Haskell can be similar to C if you do it well.
Yeah. First of all, being similar to C is quite a challenge, because C is very fast. C is very close to hardware. Actually, C was developed from the hardware, and taking the assembly language and lifting it a bit to the next level of abstraction. Haskell comes from another direction. Haskell was designed by mathematicians on the math was taken as an origin. Say, okay, in math we do things like this. Let's do the same in programming. So the way of development is, let's take math and then let's bring it closer to hardware. So Haskell is very high in the abstraction level, very high in the abstraction level, which is why you need we need 10 times less code to express an algorithm, because it's very high in the abstraction level. That's first of all. So the comparing head-to-head Haskell and C may not be a fair comparison. It's like comparing bicycle with a truck. Yes, who is faster? Oh, no, a motorcycle with a truck. Who is faster? Yes, but we still can compare, of course. Now, when you write imperative code, you have in C you have several advantages. What are the advantages? You manage memory manually, and this allows you to be very effective, more effective than garbage collector. That is in Haskell makes automatic memory management with garbage collector. You could write more performant code manually as a garbage collector. That's first. That's what C allows you to do. Second, you can manage all the computation in C very close to CPU, so you can you have access to pointers. You can manage which memory is copied where. You can optimize on this level. You cannot do this optimization in Haskell. What you can do, but in Haskell, there are other stuffs that you can do in Haskell and you cannot do in C. For example, because Haskell has no side effects, you can easily eliminate a lot of computation when you don't need it. You can postpone computing stuff somewhere later with no impact on the correctness. And anytime the result of the computation was not needed, it was not computed. And then you save a lot of compute time. And this is not possible in C. So you could write some code in Haskell that would outperform C 20 times faster because of this execution elimination. And there are benchmarks where Haskell outperforms C like 20 times faster, but the people say it's not a valid, they don't relate to it as a valid result, because they say, yeah, of course, by eliminating computation it can be faster. On the other hand, when you take some code where there's no such an elimination, or it's not possible because of the algorithm, and you compare head to head, Haskell would be 20% slower, which is not a big deal, by the way. If optimized, if well optimized, 20% slower is, I don't think it's a big deal. It's not like 2 times slower or 10 times slower.
Yeah, I would like to add the answer. So by my experience, yeah, C is pretty much faster, or even 20% much faster. But at the end, you realize that your program, most of its runtime, just waiting for database I/O. So why do you need such speed waiting for database? And yeah, for me, it makes sense to implement such, I don't know, some performance, how to say, if you need to implement some algorithm and you need the algorithm to be very performant, it makes sense to write it on C. But nowadays, with modern applications complexity, I believe it's almost impossible to write such big applications on C. So it would be a disaster.
Yeah. Also, I mean, you probably have 1% of your code that executing this critical performance part, and 99% of the code is not performance critical at all.
Yeah, and I would add what functional programming for me, yeah, I think everybody understands that from business perspective, this mathematics means basically nothing when you go to your manager or boss and say, okay, let's use Haskell or whatever, and try to argue, telling that, okay, it's based on math, it's pure, it's nice, and whatever. It's not argument for your boss, right? Because it doesn't bring business value. So I think we should operate other words like, let's say, resilience. And one thing, maybe I missed, maybe I didn't hear, that nowadays we write concurrent applications, and concurrency is one of the main problems. And we face this problem because CPU don't grow. They stopped at some level, and from some point CPU started to add cores, and we have basically more and more cores. And to use all of these cores, we run our application concurrent. And from this, for example, Java started to face a lot of troubles because of mutability, because different threads share mutable data, and we end up with deadlocks, live logs, and just logs, and one thread waits for another to unlock and stuff like that. They just basically waste resources. So and functional programming solves this problem. Immutability solves this problem. If you don't have mutable data, so you don't have you have nothing shared between threads. Threads could share data. It's immutable. It's guaranteed. So it's guaranteed immutable. You don't need to lock on it. You can only read it, and that's it. So minus one problem at least. And yeah, another problem is green threads, so to say, or coroutines in Kotlin and stuff like that, or just which light threads it's called also. Yeah, and yeah, functional programming helps here also to basically to write concurrent applications and safe. I think the most important, concurrent and safe applications. Yeah.
Yeah, thanks for sharing. Thanks for sharing. By the way, we would be doing these meetups as a series. And on what topic would you like to have the next meetup? Is there a topic in functional programming that you would like to hear about in the next meetup?
Yeah, maybe I can suggest something. So yeah, to be honest, I saw Haskell first time on this meetup. It was interesting, but yeah, for me it looks like kind of alien language, because it's very different from other popular languages. So maybe we can pick some more popular languages, more common, with a strict type system, maybe TypeScript or whatever. Because, for example, TypeScript could be used, more people could use it in kind of daily basis. It's easier to start with. And maybe using, not exactly TypeScript, maybe other one, but just pick one popular language and try to explain how is it possible to apply functional programming to help people. Because for me, I believe it's really hard to move to Haskell or even Scala. It's nice languages, but pretty rare and hard to find a job. Yeah, and maybe something simpler, but people could start explore this, maybe apply on their daily basis some approaches from functional programming. That's the idea.
Got it. Thank you. Anybody else?
I would be interested in watching or experiencing how to build an actual app mobile app or a web app or something like this with a user interface and user input and output, and to apply these principles in a very normal day-to-day use case.
Anybody else?
For that, I think I would really recommend the Elm tutorial. They have a simple example that I've looked at.
Yes, yes, Elm is a good way to, if you want to do UI with functional languages, is a very good place to start. By the way, Alexei, I wouldn't recommend learning functional programming with an imperative language like TypeScript, because it is possible to use functional programming in TypeScript, but it's more verbose. Sometimes, in order to express a functional concept in TypeScript, the code is going to be much longer as doing this imperatively. And from the first time, the functional way would look unnecessary. So I don't understand why should they do this long code? How come it simplifies anything if it complicates it? If you just learn the functional programming in a functional language like Elm, for example, and then you understand the principles, then you can apply the principles in PureScript. Then it's going to be longer, but now you understand why. You understand why it is so. What do you achieve with this?
Yeah, that's true. I completely agree with that.
Yes, I
By
can
the
also
way,
confirm I tried functional programming with C++ and Rust. And for example, you could say I replace my for loop with a recursion, but it's less efficient because you have additional function calls. And I think compilers very often optimize for tail calls, but no compiler guarantees it. So you could have a Stack Overflow with your tail call.
yes, there are practical problems which are solvable by using tail call optimization. Or you could, if you're in C++, you could create some primitives like map, fold, reduce, implement the primitives with a for loop inside, but then use the primitive. Then you could looks functional, at least outside this map, and runs the same speed as a loop. What I wanted to say also is that Haskell it's very different, and that's why learning Haskell it takes time. It takes time to learn because it's very, very different, but it's very simple. The language itself is much simpler than the imperative languages. By simple, I mean Haskell has much less language features. You have function definition, function calls. This is and pattern match. This is what you have there. There's not much more. And out of all this, you build the whole program. In imperative language like in Java or Scala is also, or C++ is a good example. The language is huge. You have so many things there inside. You have object, you have inheritance, you have properties, accessors, setters, getters. There's so many things. And you need to learn everything. in Haskell, it's simple. It's very simple. And the same principle applies again and again. You learn one thing and then it applies again and again in the macro level and in the micro level. And that's why it's simple, because it's the same stuff. C++, no. One thing in the macro, another thing in micro, another 10 things in micro. You can do it this way and this way and this way. And yeah, the complexity grows. So, so my question is, shall we complete, or do you want to share something else? Or let's make another question or another share and then complete the call. Okay, nobody asks anything, so I guess there's nothing more to say. So I thank you for being for being here. I invite you to join our next meetup. So we do the meetups in person in Munich. And so if you can be in Munich, come to our in-person meetup, and then we repeat the same meetup online for people who live outside Munich. So that they can participate, and we're going to do it as a series of meetups with different topics, which build one on top of the other. Please bring your friends, because we want to build a community of like-minded people, of developers who are interested in functional programming. So community is important to get, if you want to be successful with this stuff. And you could ask friends technical questions, of course, one another, and how they, for example, how they convince their bosses to use functional language in workplace. Just share experience with one another. So we will be also in future creating as a forum, as like Stack Overflow, where you could register and ask the people you meet here in the meetups the questions online, questions answered. I'm also going to be there. Please be active in the community. Now we have meetup. You could message one another there. Please, in the meetup, also update your profiles with your names, your contact data, so that people can contact you, and in this way we create a community which helps all of us to grow. Thanks a lot, and I will complete the call, and see you next time.